Hello! In this video, I will be demonstrating how simple the process of automating the UNI-T 900 series wave generator is using PowerShell and standard software controls. So please, join me. This project started with my need for a dual-channel arbitrary waveform generator with a frequency counter. While researching waveform generators for this purchase, I noticed that the device that I was leaning toward purchasing had programmability listed as a feature, and this intrigued me. And this is the device that I decided on. The UNI-T UTG900 series arbitrary waveform generator is a complex little device having quite a few options that need to be configured prior to performing any test. For instance, having to set the waveform frequency, amplitude, offset, phase, duty cycle, as well as selecting between waveform types for each of two channels. Also, in more complex cases, selecting the modulation type. This includes choosing from amplitude modulation, pulse modulation, frequency shift keying, line, and logarithm. This configurability gets even more complex if you want to alter one or more of these settings during the middle of testing. So why do we want to be able to remotely control our test equipment? Well, first, it allows us to save and call up multiple preset configurations on demand. It allows for automatic orchestration of configuration change during experimentation. And it allows us to access device settings and measurement data from our lab computer during tests. This allows us to combine frequency counter data or current waveform settings with the results measured by other test equipment such as oscilloscopes. First, we need to go over a couple of terms. The first is VISA, or the Virtual Instrument Software Architecture. This is what allows us to create sessions and connect to various devices from different manufacturers. Next is SCPI, or the Standard Commands for Programmable Instruments. This is the command language that allows us to communicate in a language that the various devices understand. I found a lot of information on device control using lab automation software such as National Instruments LabVIEW, as well as scripting SCPI commands from Python. But since I'm a PowerShell proponent, I thought I would see if I could learn to control my device utilizing simple PowerShell commands from the same workshop PC that I use for my oscilloscope. There are a couple of prerequisites that I must list. The first is PowerShell. PowerShell comes with all recent versions of the Windows operating system. Currently, I am using the provided PowerShell version 5, and I have not yet worked through the issues trying to get it to work with PowerShell v7. As this requires DLLs, this demonstration will not work natively on Linux, and is an exercise left for another day. The next prerequisite is the National Instruments NI-VISA Windows software, which can be downloaded from the link provided in the description. The last prerequisite is the programming guide for your device. I have provided the link for the UTG900 programming guide, which is the device that I will be using in this video. So we're going to start downloading our prerequisites, beginning with the NI-VISA software. I went ahead and I installed the offline version. So instead of the simple installer, I'm going to download the full 1.42 gig ISO image. As you can see, we've downloaded the ISO image, disk image file. As this is Windows 11, we can simply mount the ISO by double-clicking on it. Accept your software license agreement. It first is going to install the package manager. Now it's going to let us select which components we want to install. I don't install any of the unchecked selections, so I'm just going to go ahead and click install. Again with the license agreement. And then we sit back and enjoy the install. And 9 short minutes later, software's installed and we're ready for a reboot. I have also downloaded the UNI-T programming manual from the link provided. This document is essential as it will describe all of the commands necessary for programming the wave generator. Of particular importance are the channel commands. Here you can see an example of the output command. This is what turns the channel output on and off. Notice the format, channel, with the numeric value of that channel, followed by output, and the number 1 or on, or you can put 0 or off as the parameter. Another valuable command is the frequency command. Again, notice the format, channel, and the numeric value of the channel, the word base, then frequency, followed by the frequency in hertz. Again, it's not important to memorize these right now. You'll have access to the document when you download it, and you can look at my example code to see how I've actually used these commands. I will be stepping through the example code in 2 different segments. First, I will step through the basics of communicating with the device, and second, I will do a full run-through of an example orchestration. The first step is to load the NIVisa.NET assembly. Next, we create an instance of the Resource Manager object. This is what will allow us to manage one or more resources. Thirdly, we will run a command to the Resource Manager that will go identify all the devices attached to the system. Here you can notice the filter of $***. It has returned a resource count of 1. As we expected, there is one device that is manageable attached to the system currently. Next, we'll create a message-based session to that device. As we only have one device, we'll be accessing it via index 0, which is the first instance. If there was multiple devices attached to the system, we would go through the list and identify which device we wanted to create the session to. But again, as we only have one device, we'll be just accessing that one directly. Now let's return some information about that device. We'll look at the manufacturer name and the model name. As you can see, it reported it as a Unitrend UTG900E. This is what I expected. Now we will query the device directly and ask for some identifying information. We are sending the identity command. And that has returned additional information, including the serial number of the device. As I already know this is the serial number of my device, we could continue on, but I will go ahead and show you how I determined what the device serial number is. On the waveform generator, we will go into the Utilities menu and then select System Information. And here you can see the serial number, which matches up to the information that we saw from the query. Next, I will show you the process of sending commands and querying the results from those commands. Here is an example of requesting the current value of the frequency of each of the channels. You can see that the process is to send a raw I/O write with the command from the documentation to request the value of the frequency of channel 1. Then we'll do a read string and return that to the console output. We'll do the same thing for channel 2, sending the write command and reading the result from the device. Currently, you can see channel 1 is reporting that it is set to be a frequency of 1 Hz, and channel 2 is set to be a frequency of 2 Hz. As another example, we're going to check the current phase settings for channel 1 and channel 2. We send the output command, channel 1 base phase, ? That means return the current value of the phase. Then we'll send channel 2 base phase as a command to return the value for channel 2. And in both cases, we'll do a read string after sending the command. So you can see from the result that channel 2 is 180 degrees offset from channel 1's phase. Before running the entire script, let's go ahead and look at what it's going to do. First, we're going to set both channels to a steady state. We're going to turn the output off, set the base frequency to 1 Hz, set the offset to 0 volts, set both channels to be in same phase, and set the waves to be sine waves. Then we are going to set channel 1 and 2 output on. We're going to invert channel 2, set the base frequency of channel 2 to be 2 Hz. We're going to set channel 1 offset by 2.5 volts, and then set channel 2's offset also by 2.5 volts. We're going to re-invert channel 2, set channel 1's wave to be that of a square wave. We're going to change the phase of channel 2 by 180 degrees, and then we're going to set both channels into an off state. So now we put everything together for a demonstration. We have the oscilloscope in the left window. We'll have the PowerShell script running in the top right, and we have a live view of the UTG arbitrary wave generator in the lower right corner, so we can see it all operating together in tandem. When we run the script, it will put everything back to a baseline configuration, turn the outputs on, and then we start changing parameters on the waveforms. You can see we inverted channel 2 first, then we changed the frequency of channel 2, increasing it, changing the offset of channel 1 by 2.5 volts, and then matched it by moving channel 2 down by 2.5 volts, re-inverting it so both waves are now from 0 to 5 volts. Then we change wave 1 to a square wave, change the phase by 180 degrees on channel 2, and then both channels are shut off. So you can see how everything worked together using our scripting. You will be able to download the simple example code from my GitHub repository. I will provide a link in the description. Additionally, I will provide some actual code that I am writing to support my various testing scenarios. Hopefully this video was informative and demonstrates the value of orchestrating lab equipment using PowerShell, Visa, and SCPI. Thank you for watching.